Okay, so in this movie clip, I'm going to give you some more great details on how to get the emitter current and the collector current, IE and IC. Well, definitely the emitter current IE is I E sub n plus I E sub p, and the collector current IC is definitely ICP plus ICN. As you know, this is a collector current by hole, that is a collector current by electron. Okay, so in the last movie clip, we have briefly went over uh, how to get the IC and IE, or in other words, these are four current components, IE and IEP, ICP and ICN. How to get those four different current component to address it, or to get those four different values. We should go back to the PN junction diode analysis again. So for a given PN junction diode, once forward bias is applied, then the minority carriers are injected into the other side and they are going to diffuse out. So to explain how those injected minority carriers are diffused out in the quasi-neutral region, we have used the second order differential equation, which is named as what? Minority carrier diffusion equation, right? So to solve the minority carrier diffusion equation, we should first find out the excess minority carrier concentration, which is denoted as delta sub En or delta P sub B and delta N sub C. So that is, the emitter is definitely p-type, right? Since we are talking about the PNP BJT. So emitter is p-type. So in the p-type region, the minority carrier is definitely electron. So excess electron concentration in the emitter. And base is definitely n-type. So minority carrier hole, how much hole concentration has been increased or decreased. So we would like to know the detailed information, how much excess hole concentration has been obtained in base region. Well, similarly, in the collector region, which is another p-type region in PMPBJT, and the minority carrier electron and excess, right? So excess electron concentration in the collector region, we would like to know it. Once we write down the equation for each, this and that, then we can simply plug in the excess minority carrier concentration into what? Yeah, into the equation for diffusion current. So as we have learned, the diffusion current can be obtained by the doping concentration gradient along the x direction, right? And you can multiply unit charge, cross-sectional area, and diffusion constant or diffusivity. Okay, then once we get those four different current components as a function of x here and there, these three different new coordinate system, right? Always x prime, x2 prime, x single prime, and the original x-axis indicates how the minority carriers are diffused out. So diffusion, the direction of minority carrier moving is denoted as a new coordinate axis system in each region. Again, emitter, base, collector. Okay, then afterwards, we're gonna add up hole and electron current components together. Then we're gonna get the terminal current of BJT. I mean the emitter current, collector current. Then since IE is equal to IB plus IC, IB is base current. So since you know those are two current components, IB is very simple, right? Just to take IE minus IC is equal to IB. Okay, that was our game plan for current voltage derivation in PNP BJT. So in this movie clip, let me give you some more detailed analysis for each region. So emitter region, base region, and collector region. So let's move on to the first region, emitter region. So previously I mentioned that the PMP BJT can be worked in active mode. So the meaning of active mode indicates emitter-based junction is under forward bias. However, the collector-based junction is under reverse bias. Since we are talking about the emitter, so this emitter-based junction is under forward bias. So simply that is P plus and that is N. So one side is the PN junction and this is now forward biased. So as we know, many holes would be injected into the base region. But since this lecture title, take a look at it, emitter region, right? So many electrons is going to be injected into the P side because this is forward biased junction. So how these injected minority carriers are diffused out. So the direction for X2 prime should be aligned to the direction of minority carrier movement in the emitter region. So that is the reason why X2 prime is indicating to the left-hand side. So now to explain physically how those minority carriers, which is electrons in the P plus emitter region, is diffusing out. So take a look at this minority carrier diffusion equation. Okay, well basically on the left hand side that was a d delta n sub e dt, and since over time the excess carrier concentration is not modified at all. Why is that? Because we have applied the DC voltage, right? So DC indicates the certain amount of minority carriers can be steadily supplied from N side into the emitter P plus side. So since because of that, delta N of sub E with respect to time variation is 0. Well, everything that I'm talking about has already been discussed in PN junction diode theory. The only difference is the word. Instead of P side, I'm using emitter. Instead of N, I'm using base. Okay. If you cannot follow up, catch up all the contents that I'm talking about currently, please go back to the PN junction diode theory again and review it thoroughly. Then please come back to this movie clip. Then you should be very happy and easy to understand. All right. So by solving those diffusion equation, minority carrier diffusion equation, we're gonna get the solution. But since this is a second order differential equation, the general solution form should be given as follows. Then to get the specific solution for this minority carrier diffusion equation, we should know two coefficients named as A1 and A2. So for that purpose, we should develop two boundary conditions. So go back to this forward bias, the emitter-based junction, and with respect to when it comes to the injected electrons, what kind of boundary conditions can we get? Yeah, this and that. When x2 prime is 0 or x2 prime is infinity. So herein x2 prime is 0, that means x2 prime is approaching to the infinity. How much excess electron concentration in the emitter should be left behind? Well, definitely 0. Why is that? Because this is a P plus region, so many holes are available. So since many electron has been injected from N side, because this junction, emitter-based junction, is forward biased, so maybe in this regime, the electrons would be still survived, whatever the electron hole concentration is very high or low, it doesn't matter. Many electron is still supplied from N side. But the question is here, right? If and this physical distance is very long, infinity, then maybe many holes or almost electrons would be recombined with holes in emitter region. So nothing would be left behind at x2 prime is 0, infinity. So that is the reason why at x2 prime is infinity, the excess electron concentration in the emitter should be 0. Okay, so we found one boundary condition as it is. And next one is this. Let's take a look at the excess electron concentration in emitter at the edge of the depletion region of emitter base junction. I'm talking about here, right? So for the given extra prime of 0, how much excess electron concentration can be obtained and supplied from the N side or base? As we have already learned in the p-n junction diode theory, the, the electron concentration in emitter side, I mean the minority carrier concentration at thermal equilibrium, times this. In p-n junction diode theory, that was denoted as V sub A, applied voltage between P and N. But since now we are talking about the emitter and base, so the voltage difference between emitter and base is denoted as V sub EB, right? VE minus VB, right? So instead of VA, I have used the V sub EB. That's the unique, only difference. Everything is quite similar to the excess minority carrier equation in p-n diode theory under forward bias. Okay, so since you know those are two boundary conditions, please plug in those two boundary conditions into the general solution. Then you're gonna get the two coefficient A1 and A2. Well, definitely extra prime is approaching to plus infinity, and this whole value should move to the uh, approaching to the plus infinity, but left-hand side value should be 0. So to satisfy this equation, A2 should be 0. So you can ignore the second term in the end. And A1, by plugging in the extra prime of 0 value here and there, you're going to get the A1 is identical to this boundary condition. So from the general solution, we're gonna get the specific solution for the minority diffusion equation to be valid for this emitter reason. So n of delta n of e, delta n sub e of x2 prime is equal to this. Okay, we're almost done. This is not the final goal. The final target is we would like to know the emitter current induced by electrons. Okay, so I sub En is equal to the some coefficient times what? Yeah, excess electron concentration gradient. So you should take one derivative. Okay, so just plug in the delta N of E, the equation above here into here, and take one single derivative and plug in the 0 value into the x2 prime. Okay, you can do that. Since this is constant with respect to x2 prime. However, this guy is the function of x2 prime. So take a first derivative of it, and maybe minus 1 over L of E should be jumped out, right? So, and that minus 1 over LE would be multiplied with this coefficient. So minus minus would be canceled out. So in the end, the QADE divided by LE. You can see that here. And then N sub E naught is a constant, right? So that is still alive here. And the left of it is still alive here. Okay, so we all set IE naught, IEN, the emitter current by electrons would be described with this equation. Okay, so from now on, we're gonna repeat this analysis for base reason as well as for collector reason. So let's do that. I guess, yeah, before moving to the base reason, let's go to the collector reason first because it is much simpler. Um, in the collector reason analysis, since this PNP BJT is operating under active mode, so this base collector junction is reverse biased. Okay, so this is quite different from the emitter reason analysis. So uh, first, let's write down the minority carrier diffusion equation here in the collector reason. So herein, the electron would be injected into the, not injected actually, many randomly generated electrons near the edge of depletion region would be likely to be injected or to simply move into the depletion region. And since a built-in electric field formed in this depletion layer can help to have those electrons to be drifted toward the p side. So in the end, this electron movement can be observed. And once electron has been arrived in the collector region and it's going to be diffused out. So for that purpose, we have learned this. Well, definitely this new coordinate system x prime is well aligned to the diffusion direction of minority carriers in collector region or p-type region. So along the x direction, let's draw the axis delta electron concentration in collector region as a function of x prime. What is it? If Again, if this base collector region is forward biased, then definitely this delta n sub c would be this positive value, and in the end it's going to asymptotically approaching to the zero value, right? But since this BJT is working in active mode, so that base collector junction is reverse biased, so that many uh, if I draw the delta n sub c in the collector region, it should be like that. If you're not familiar with this uh, access carrier profile in the collector region or p-type region under reverse biased p-n diode, please go back to the, maybe a few movie clips talked about this. Okay, so this access electron concentration profile can be obtained when collector base voltage difference is negative. I mean, the base collector junction is reverse biased. Okay, well, just for your information, what if the base collector is forward biased? Then this value would be what? Yeah, Ni squared divided by N sub, in this case, collector, and exponential Q times V sub CB collector base divided by KT minus 1. Okay, but since V sub CB is negative, this all value is a negative 1, so that this value here in the excess electron concentration is smaller than 0. Okay, so with that in mind, again, let's solve the minority carrier diffusion equation for those electrons. So to explain the physical behavior of those electrons or minority carriers in the collector region or p-type region, we should set up another minority carrier diffusion equation. And the reason why the left-hand side is 0 is again, d delta n sub c dt is 0. Why is that? Because we have applied the DC voltage. Okay. And now let's solve this second order differential equation. So for that purpose, let's set up and propose the general solution first as follows. And again, we should know and find out those two coefficients, A1 and A2. So to know those two coefficients, we should set up the boundary conditions. So go back to the cross-sectional view again here, and the boundary is here or there. So when x prime at x prime of 0, how much excess electron concentration in collector region is left behind? So just bring this equation, and definitely this V sub CB is currently negative value, so this whole value is negative. Okay, and another boundary condition is the other side edge right here. So x prime is infinity. But as we know, once electron has been injected into the p side, and it's going to be recombined with many holes in the collector region. So at x prime is infinity, nothing would be left, nothing would be survived. Okay, no electron would be survived. So that this delta n sub c value should be 0. Okay, so we got two boundary conditions and plug in those two boundary conditions into the general solution, and we're gonna get the A1 and A2. And in the end, we're gonna get this. Okay, just for your information, plug in the uh, infinity value into the x prime here and there. Since this is a plus, so everything is very plus infinity. But left hand side, if this is infinity, then the left hand side is 0. So 0 is equal to something plus infinity. So to satisfy this equation, A2 should be 0. So now you can ignore the second term. And A1 can be simply obtained by plugging in the x prime as 0 value. Okay, exponential to the 0 is equal to 1, right? So A1 times 1 is equal to what? Yes, this guy, right? Because x prime is 0, the whole value is identical to here. All right, so the specific solution for the minority carrier diffusion for collector reason is this, okay? And now, it's as a second step to know the collector current by electrons, you should set up the diffusion equation, right? So some constants value times the access electron concentration gradient, right? Gradient means the first derivative. So just simply plug in into here, and since NC not exponential QVCB over KT minus 1 is a constant with respect to the x prime. No x prime here and there, right? So this is simply constant. And take a first derivative of it here. So minus 1 over L sub C should be summed out right here once you take the first derivative of it. So minus 1 over L sub C. So minus 1 over LC. And the QADC is still here. Okay. And since we would like to know the ICN at x prime of 0, so plug in the x prime 0 value, then everything is simply 1. Okay, so those two terms would be survived, and you're gonna see that. Okay, so in summary, collector reason analysis is almost identical to the PN junction analysis under reverse bias. Okay, all right. I guess it's a good time to have a short break time here in. So please have your own short break time, and see you in the next movie clip. Bye bye.